Okay, ladies, welcome to the second lecture of the dental public health content that we're going to be looking at today. I'm actually doing this for the second time because on Friday morning, I thought I was recording this, and so I spent an hour basically talking to myself. Got so frustrated, I thought, okay, I'm not going to do any more for Friday, so that's why I'm here today on Saturday afternoon trying to figure out how to do this, to get it posted so that you can watch it. Yes, I am admitting that I'm a computer illiterate old person, but okay. All right, we had stopped with our first lecture presentation at this point, the probability levels, where we had talked about when you're talking about a probability level, you're really talking about the level of significance for testing your hypothesis or your null hypothesis, whichever one you decided to go with. Now, what a probability level or a p-value is, that sets the level of acceptable chance that a study sample will show a difference or will show a relationship between the things that you're looking at, even when there is no difference or that the study sample is not representative. So that means basically you want to set your probability level at less than 0.05. If your probability level comes out, if you plug your numbers in and your probability level comes out at less than 0.05, that means that there was a difference, a statistically significant difference or relationship between the two variables that you're looking at. Those variables could be incubation periods for diseases. They could be national board test scores for two different groups of individuals. They could be in regards to stress level for dental hygiene students and their opinion of their profession, the last semester that they're in the program. So everything needs to be set at 0.5 or below, really less than 0.05. In many cases, the lower you get of a probability level under 0.05, that's really the better because that shows that there's even less of a chance that whatever you did in your research was affected by something outside, some other variable outside of your research. The thing you need to remember is if your probability level is 0.05 or greater, you're basically saying that your results were not statistically significant. Now, when we talk about statistically significant, remember there's a difference between when we talk research, in the lab, a statistically significant difference, and then we talk clinical results. Remember when we talked about Arrestin and the level or the amount of pocket reduction or increase in attachment? Arrestin in the lab, there is a statistically significant relationship between the use of Arrestin and the reduction of a pocket depth. But when you get out into clinical practice, is that 0.5 millimeter reduction going to be clinically significant? So you have to keep that in mind also. Now, with your p-value that is equal to or greater than 0.05, what happens with that when you say there is no statistically significant relationship between the two things or the three things or the variables that you're looking at? Then you're going to agree, if you set up a null hypothesis, you agree with that null hypothesis because the null hypothesis, you basically said there is no relationship. So you want to get a p-value that is 0.05 or greater because then that will prove your null hypothesis. You're proving that there is no relationship between two elements or two variables. If you have a null hypothesis and you get a probability level that is less than 0.05, you get a 0.03 or 0.04, and you've said there is no relationship, well, that probability level is telling you that there is a relationship, and so you have to reject your null hypothesis. And again, the lower probability that you get, the better your research. It looks like the better your research is because basically what you're saying is there's less than, say, a 5% chance, or if you set it up at 0.03, less than a 3% chance that something outside of your research parameters affected your results. So there's less than a 5% chance that something else interfered with your research and you got these results not due to your research parameters, but to some other outside or external element that had an effect on it. Now, at the same time you're looking at probability levels, you also are going to look at confidence intervals. These correspond to your p-values. In other words, if you've got a p-value that is less than 0.05, that means there's less than a 5% chance that the observed results were due partly to chance, due to something outside of your control. You're also saying at the same time that you're confident, you're 95% confident that your results were not due to some outside element. That's your confidence level. So let's talk about this and kind of work our way through, because the National Board will probably ask you at least one, maybe two questions in regards to your probability level or your confidence interval. So we look at this example. We have a statement of the problem. Relationship between clinic requirements and senior stress levels is unknown. Now, with this, you're going to set up either hypothesis or null hypothesis. Say your null hypothesis is going to be Clinic 4 requirements have no effect on student stress levels. Now, that's not how you're going to feel. You, as a senior dental hygiene student going through Clinic 4 requirements, you're probably not going to go with a null hypothesis. You're probably going to say, no, there is an effect on our stress levels. So, we're going to say there is it's a hypothesis. There is maybe Clinic 4 requirements increase student stress levels. But if we look at this statement right here, we know this is going to be a null hypothesis. So we set the p-value as being less than 0.05, right? And we actually get a p-value that's 0.03. So what does that mean? 0.03 is less than 0.05. So is that going to indicate a statistically significant or a non-significant relationship between stress and clinic requirements? So we know that if it's less than 0.05, we're showing that there is some type of a relationship between the two. If it is greater than equals 0.05 or greater than 0.05, then that's telling us there's no relationship between them. So if we've got a 0.03, then we're going to indicate what? Is it statistically significant, or is it a non-significant relationship between stress and requirements? We're going to say it's statistically significant. Now, we hypothesized that there was no relationship. So we said there's no relationship. Are we going to accept, or are we going to reject the null hypothesis that we set up? Okay, this is going to be 0.03 is less than 0.05. And if we get a p-value that is less than 0.05, there is a statistically significant relationship between the variables that we're looking at. So that means that if we had set up a hypothesis, we'd agree with the hypothesis. But because we said it was null, there's no relationship. And because it is less than 0.05, there is a relationship, we're going to reject the null hypothesis. And so I'll ask you questions, the National Board will ask you questions along this line to where you'll have to identify whether or not you're going to accept or reject, say, a null hypothesis, or if they set up a hypothesis, if you would accept or reject. If we had said here, Clinic 4 requirements have no effect, or Clinic 4 requirements have an effect on student stress levels, then that would have been a hypothesis. And then if we had gotten a 0.03 probability level, then we would have accepted the hypothesis because we said there was a relationship. We know if our probability, our p-value comes in at less than 0.05, that our numbers are showing there is some relationship between what we're looking at. And we said there was a relationship. We said Clinic 4 requirements increase student stress levels. Then we would accept that, accept the hypothesis. So let's look at this one. Statement of the problem, the relationship between brand X and tooth whitening is unknown. And we come up and we say brand X significantly whitens teeth. So we're saying there's a relationship here, right? That brand X has an effect on whitening teeth. So are we going to say this is a hypothesis or a null hypothesis? We're going to go with a hypothesis. Now, say we want our p-value to be less than 0.05. And we get a p-value that is 0.07. Now, we hypothesized that there would be a relationship, right? But this P07 indicates that there's not a significant relationship between brand X and tooth whitening. So with this, are we going to accept or reject our hypothesis? We're going to reject our hypothesis because we said that there was a relationship, and a p-value greater than equal to or greater than 0.05 means that there is no relationship. Now, what if we had set our p-value at 0.04? If we set it at 0.04, does that indicate a statistically significant relationship or a non-statistically significant relationship? It's less than 0.05, right? So that's going to indicate a statistically significant relationship. And so in this particular situation, we hypothesized that there was a relationship. So are we going to accept or reject our hypothesis? Hypothesis means you're saying there is a relationship between something. We've got a p-value that is less than 0.05, when that indicates statistically that there is some type of a relationship. So we can accept our hypothesis and saying that brand X, there is a relationship between brand X and tooth whitening. Now at this point, we're hypothesizing maybe we could have said that brand X significantly whitens teeth. We're saying that it increases, that's the relationship, that we use brand X, we're going to get whiter teeth. Okay, let's look at another example here then. Statement of the problem. The relationship between brand X and tooth whitening is unknown. And then we're going to say there is no statistically significant difference between brand X and a placebo when comparing tooth whitening. So we're basically saying that with this particular statement that brand X has no effect on whitening. Okay, so is this a hypothesis or is this a null hypothesis? It's going to be a null hypothesis. We're saying there's no difference between brand X and a placebo. Basically, if you forget the placebo, you can say no difference between brand X and tooth whitening. So we get a p-value that is 0.03. This indicates what? There is a statistically significant relationship because 0.03 is less than 0.05. That's that maximum probability level. So are we going to accept or are we going to reject our null hypothesis? Okay, we said there is no relationship with a null hypothesis, but yet this p-value shows us that there is a relationship from the statistical manipulations, from the numbers that we plug in. So for this situation, we're going to reject our null hypothesis. Now, say we had a p-value that came out 0.06. What do we know? 0.06 is greater than 0.05. So anytime it is equal to or greater, there is no statistically significant relationship. So we say here, there's no relationship. We had a null hypothesis that said there was no relationship. There was no difference between brand X and a placebo in tooth whitening. We're basically saying brand X has no effect on tooth whitening. So are we going to accept our null hypothesis? Or are we going to reject it? We're going to accept it at this point. We're saying the numbers are telling us with that p-value of 0.06 that there is no statistically significant difference. That's what we said. There was no difference. There was no relationship. So we accept that null hypothesis. Now, let's make things a little more complicated here, and they'll also ask you probably at least one question regarding a type 1 and a type 2 error. When we talk about type 1 and type 2 errors, we're talking about the null hypothesis only. So you're not thinking about the hypothesis. You're only thinking about null hypothesis. Type 1 error is where you conclude that the null hypothesis is false when it's actually true. So a type 2 is going to be you conclude that the null is true when it's actually false. All right, so we have a null hypothesis. Brand X has no effect on whitening. P-value of 0.03 means what? There is a statistically significant difference. So what are we going to do here? We are going to reject our null hypothesis. So we're saying that the null is false because P is less than 0.05. So brand X has an effect on tooth whitening. Okay, now what if we say that brand X has an effect, and that way we're concluding the null is false, but really brand X has no effect, so the null is true. That's a type 1 error, which means you're concluding that the null is false, and you're saying, okay, we're not going to use brand X to whiten teeth because research or this study has shown that brand X has no effect on teeth whitening. So we don't use that product at all. We don't recommend that product. When actually there was a problem with the research, either the sample selection, what they did, how they ran the research study, and so they ended up with a type 1 error. They said, they agreed with the null hypothesis. There is no effect in terms of, we said there was no effect when actually if somebody else, and what happens is somebody else will run the research. They'll do another study and they come up and they find out that, okay, we said it didn't have an effect, but then our numbers came out and said, yes, it did have an effect. There was a statistically significant relationship. And so we're not recommending the product. We're not looking at the product anymore. The company comes back, they do another research study, and they get the reverse. They figure out that, okay, there is no relationship here. Okay, this first research study, there was a problem with the study, and there is a relationship. Maybe brand X does whiten the teeth. And so here you have a product that actually works, but nobody's recommending it because they're going by this first era, a type 1. So what we're looking at then is, with this case, a type 1 error where you said that your null hypothesis had no effect, you end up with a type 1 error, meaning that, okay, the null was wrong. There is an effect. And so then, you go on, you're not recommending a product. Somebody does another research study and they figure out that, okay, we didn't get the same results. That, yes, we say there's no effect. And our p-value was 0.07. 0.07 agrees with the null hypothesis. 0.07 means your probability level, your p-value is greater than 0.05. Equal to or greater than 0.05. So there is really no relationship between brand X and tooth whitening. So they come in and they say, okay, no, your original research was wrong. So what we have been doing in terms of this is with the type, a type 1 error, where in the past we said, okay, there is a relationship, so we will recommend this. But a type 1 means that the null is really true, meaning that there is no relationship. So we could be recommending a worthless product. Now, to compare this to type 2, and I think it's easier if you think of type 2 to try to remember which of these is which. I always remember that with a type 2, you're considering the null hypothesis is true. You're concluding that it's true when it's actually false. So if you say the null hypothesis is true, there is no relationship, when actually there is a relationship. You have to remember between these two, because they'll ask you a question, they'll give you an example, and they'll ask you which type error has occurred. Remember that, or the way I remember it, is a type 2. 2, T for 2, T for true. So if you remember, you conclude that the null hypothesis is true when it's actually false. Then you can always remember the other one is, okay, we conclude it's false when it's actually true. So remember the type 2, the T's for type 2. T for 2, T for true. Null hypothesis is true when it's actually false. So you have a p-value here. You're saying that the null brand X has no effect on whitening. We end up with a p-value of 0.06. That tells us those numbers that 0.06 is greater than 0.05, so there's no relationship. So originally then, if we said brand X has no effect on whitening, and we get a p-value of 0.06, that's telling us the numbers are saying there's no relationship, we're going to accept the null hypothesis. So we're saying that the null is true. Brand X has no effect on whitening because of this p-value that we got. Type 2 error means that you conclude the null is true when actually the null is false. So again, remember, type 2, T for 2, T for true. Null is true when it's actually false. And what happens with this then is you can overlook a good possible treatment or a product for that. As far as that, we could go into this much more in depth and talk about how it affects your research, how you end up getting to that. But, you would have to take an entire semester on stats in order to really get into this stuff. I think that the information that I've given you here will be enough to answer whatever questions I throw out at you or the National Board throws out at you. Okay, so we've been talking about the scientific method, where anytime you conduct some type of a research, there are a series of steps that you have to go through. And the first step was that we had a statement of the problem. You say the relationship between fluoride and dental decay is unknown. And then you come up with a hypothesis where you basically you're guesstimating what you want to do, right? So the third step is collecting the data. And in collecting the data, you've got the literature review, and you're going to develop your research methodology. So where does this fall in? We said the first step is statement of the problem. Second step is hypothesis or null hypothesis. There are individuals who will group these three things: your literature review, you develop your literature plan, and then you collect the data. They'll group that into just the one step, collect the data. I want you to be aware that there are kind of three substeps in there in the event that the National Board asks you a question and they give you one or more of number 3, 4, and 5 selections, and you have to kind of put it into order based. They don't give you just one collect the data number. They give you 8 steps instead of just the 1, 2, 3, 4, 5, 6, 7 steps that we're looking at, okay? 5, 6 steps that we're looking at. I can't count. So I want you to know kind of where that fits in there. Now, when we're talking about collecting the data, you do your literature review first. So what you're going to do is you're going to go out there and you're going to investigate to see what has been done previously, what kind of information has been collected previously. And you've got that and you look at that. And then you determine what other information you need to find out, what you're looking at. And that's where you actually will develop your plan. And that's kind of like assessment on the research area in terms of you've got to collect some information, you've got to develop your plan for how you're going to collect more information. And once you've developed your plan, you go out and you collect your data. Now, when you're collecting your data, you have to, again, we're looking at sample selection. You're going to go out and if you're trying to do a research study that is going to have an effect on 100,000 people, you can't go out and you can't assess or survey 100,000 people. So you're going to have to pull a representative sample of your population. And we've talked about when we pull these samples, what all is involved. And we want to use probability samples, right? We don't want non-probability because they're too subjective. Probability, how we select our samples, is going to be based on simple random, stratified random, or cluster samples, what we're looking at. What we do in terms of a research study like this is then we're going to basically assign our samples or our members of our samples to either an experimental group or a control group. Because what we're doing at this level, experimentation or the experimental research, is now we're trying to find a cure or a treatment for something. So we need to have 2 groups. We need to have the experimental group and the control group. The experimental group gets whatever it is we're trying to test. Control group serves as our control. What happens to individuals that have the same, the same disease, the same thing that we're looking at, but they're not getting the magic potion? So with our experimental group, the things we want to remember with this, the experimental group receives whatever it is, the magic potion, whatever it is that we're testing, the treatment or the product that we're testing. And the treatment or the product then becomes what we call our independent variable. And the thing to remember here is the independent variable is controlled by the researcher, meaning that the researcher controls the administration of the independent variable. And then the independent variable controls the dependent variable. So what we're looking at then is our control group. Okay, we have got our experimental group that's going to get the magic potion that we're testing, right? And that magic potion becomes the independent variable. It almost sounds like it's backwards. It almost sounds like that should be the dependent, because that's dependent on the researcher, administering it. But the researcher is going to, say, administer the fluoride. And then the fluoride independently is either going to affect or not affect whatever disease or whatever treatment, whatever we're looking at to try to determine if this is really going to work. So that's why it's called the independent variable. We don't know what it's going to do. The control group doesn't receive the treatment or the product being tested. It either receives nothing or it receives a placebo. And in most cases, you're going to have a placebo, because without that, you're going to have a problem with the Hawthorne or the halo effect. This came about, I think, in World War II in the airplane manufacturing companies, where they were trying to increase production. And so they would have efficiency experts go in and they would observe the workers to try to, cut time, cut steps so that they could get, the machinery, the parts, whatever for the aircrafts out quicker. Well, they discovered at that point in time that if the workers knew that they were being watched, they tended to perform better, or they performed different from what they normally did. So that was known as the Hawthorne or halo effect. If somebody knows that they're receiving a treatment or a product, or they're being observed. It's kind of like when you guys are in clinic and I walk up and down the clinic, I can watch. And sometimes I do it just to be facetious. If I'm bored, I'll walk up and down the clinic and watch you guys from you're crouching over your patients, really poor ergonomic positioning. And all of a sudden you'll see me go by and you sit up straight. That's a Hawthorne effect. You're being watched, you're going to perform differently. So what happens with this is that normally you're going to give your control group something. It's not going to be the product you're studying, but it's going to be something. So let's look at this. We have said that fluoride reduces the incidence of decay. That's going to be, whether we're going to have a hypothesis or a null hypothesis. If I say fluoride reduces the incidence of decay, I'm saying fluoride has an effect on the level of decay. So this is going to be a hypothesis, right? So if I look at this, is fluoride going to be the independent variable or the dependent variable? Who's going to control the fluoride? Who is going to control giving the fluoride to the experimental group? The researcher. The researcher controls giving the fluoride or administering the fluoride. So that becomes the independent variable. That becomes the thing, the product that we're looking at there. Now, if we look at dental decay, then what is decay going to be? The independent or the dependent variable? It's going to be the dependent, because what happens is fluoride is either going to increase or decrease decay or have no effect on decay. We may end up with we say that fluoride reduces the incidence of decay, and then we go through this research and we get a probability level of 0.08. That 0.08, which is greater than 0.05, tells us that there is no statistically significant difference, right? Once we get a p-value that is greater than 0.05, equal to or greater than 0.05, then we're saying the numbers are showing us there's no difference, there's no relationship. So if we ended up where we actually ran this research and we got a p-value of 0.08, we would have to what? We would have to reject our hypothesis, because the p-values, the numbers are telling us there is no relationship between the two. But we've opted to say, okay, that fluoride reduces the incidence of dental decay. So we're going to go in, we've got a hypothesis. We're going to give the fluoride, becomes the independent variable. We're going to give it to our experimental group. Our control group, then the dependent variable, the thing that is going to be affected by the fluoride, is going to be the incidence of decay. That becomes our dependent variable. That whether we see a change is dependent upon whether or not they receive the fluoride. We're going to make sure that we give our control group a placebo, something that looks, smells, tastes, exactly the same as the fluoride, so that neither group, we'll talk about a double-blind study, it's best if neither group knows who's getting what. Now, if we have a probability level that is set at 0.05, then we have to think in terms of our confidence interval, where if the confidence interval is at a minimum, really in good research that shows that something has an effect, is going to have to be 95% or greater. Because if we set it at 95%, we're saying that our p-value is going to be 5%. If we set it at 99%, then our p-value is going to be 1%. So that means there's less than 5% or 1% chance that the observed results between our experimental group and our control group are due purely to chance and not due or not a true effect that was caused by our independent variable. Our independent variable being fluoride. Okay? So this is how the researchers describe the probability of the statistical results being correct, where they'll say, here's the research we've done. We've proven our hypothesis that fluoride does reduce the incidence of dental decay, and I am 5% sure, or let's say 0.4% sure my p-value is 4. I'm saying that there's less than a 4% chance that something from the outside affected my results. My confidence level, I'm 96% confident that my results are correct, that these results, this reduction in the incidence of decay is due to the administration of the fluoride and not something else that has, affected this research or this result. Now, we also have to talk about another research design, where this is good if you're studying a particular product where you can see a difference. Now, obviously, I don't think that fluoride would be a good one, because fluoride you would need to study for too long of a period to be able to conduct this kind of a study. But if you're looking at something that prevents the buildup of calculus, either prevents the buildup or the buildup is less calcified, some type of a toothpaste product that does that, say that's product XYZ, or you've got product XYZ that does something in regards to the development. It prevents the development of gingivitis. You stop brushing completely, you rinse with product XYZ, and you're saying that will prevent the development of gingivitis in a group of healthy adults. So let's say that this is going to be, we've got our statement of the problem, which would be product XYZ's relationship to gingivitis in healthy adults is unknown. So now we said product XYZ prevents development of gingivitis in healthy adults. So is this going to be a hypothesis or a null hypothesis? We're saying that product XYZ has an effect on the development of gingivitis, right? So this is going to be a hypothesis. If we talk about the variables, then we have to say, okay, do we have an independent and, a dependent variable? What's going to be our independent variable? Product XYZ, right? What's going to be our dependent variable? XYZ is going to have effect on what? And what particular condition here, if we see a change in that condition, it's going to be dependent on our independent variable. So we're looking at gingivitis. That becomes our independent or our dependent variable. So with the crossover design, what we're looking at here is in the first 30 days, Group A receives product XYZ. So for the first 30 days of the research, Group A is the experimental group. Group B receives a placebo. So what? It becomes the control group, right? Okay. So what we do is for 30 days, we keep track of that. And what kind of index are we going to use for this? Would we use OHI index? OHI index just shows the level of debris, right? Would we use a calculus index? Calculus, we could kind of incorporate, that would give us some extra information, but that's not going to be a valid index to measure the level of gingivitis, whether it increases or decreases or, doesn't change. We would probably use a bleeding index for this. A bleeding index or a gingival index, where we're looking at inflammation, the level of inflammation and that type of thing. So for 30 days, these two groups are using either the placebo for the control group and product XYZ for the experimental group. After 30 days, we're going to get we got our baseline data, which was our pre-test prior to the start of using this product XYZ. At the end of 30 days, we're going to go in and we're going to do bleeding indexes, and we're going to compare, the difference in bleeding indexes between the group that got product XYZ and the group that did not get it. Then we're going to have a 30-day washout period, meaning that neither group is going to use product XYZ. Neither group is going to have anything special done. After that 30-day washout period, then what's going to happen is group B becomes our experimental group. Okay, group B then receives the product XYZ. So group B is the experimental group. Group A then receives the placebo, and group A becomes the control group. So you can see here how group A was the experimental group. Now group A becomes a control group. Group B was the control group, and now it becomes the experimental group. Okay, if XYZ does prevent gingivitis, we should see the prevention in both groups while they're using this particular product. And it's not just some fluke. We could say that, the first 30 days that we did this, the experimental group received this, and we had a significant reduction of gingivitis compared to the control group. Then we wash out for 30 days, we come back, and if XYZ does actually do this, if it does prevent gingivitis, then what was originally the group that got the placebo is now going to become our experimental group, and they're going to get the XYZ, and our experimental group becomes a control group, and we should see the same results here with group B. We should see a statistically significant reduction or the total prevention of gingivitis in group B. And that's kind of what you're doing with this is your subjects are serving as their own control group. And this is a really valid type of research design when you're looking at a particular product to see if that product is going to be effective. Now, we also want to talk about blind versus double-blind research studies. A blind study is where the participants don't know who's getting the independent variable and who's getting the placebo. What we're trying to do with this is avoid the Hawthorne effect between the two groups, between the experimental group and the control group, so that we don't have a situation where just because the experimental group realizes they're getting the magic potion, there could be a little bit more improvement or a little less gingivitis development because they've got a more positive mental attitude. Now, a double-blind study, this is very good, and this depends upon what it is you're looking at and trying to study. This is where neither the participants or the researchers, the examiners, know who is getting the independent variable and who's getting the placebo. And this really avoids a Hawthorne or halo effect, because in some cases, and what you're looking at is that if your researcher is administering this, the way they administer it, their mannerisms when they administer it, the individuals in the experimental and the control group can pick up on that, and that may have an effect on the outcomes of your research. You also, if you have the researcher or the examiner knows who's getting one versus who's not getting, the magic potion, that could lead them maybe to kind of mismanipulate some of the statistical things that they're looking at or record it a little bit differently because they know what's happening. And if they see during the course of the study that, one group is improving over another group and, they think, okay, well, I'm producing product XYZ and I'm giving product XYZ to the experimental group, and there's really no difference, in results between the people in the experimental group and the people in the control group, that could lead that researcher, maybe consciously or unconsciously, to kind of alter, what he's doing a little bit because he wants to basically be able to prove his hypothesis or his null hypothesis. Now, so we did all that. We collected the data, and that could be literature review, develop your research plan, and collect the data. And again, remember, step 3, they may ask you a question that just groups all step 3 into collect the data, or they may, instead of having 6 steps, they may have, 6, 7, 8 steps because they've put these in separately. And so you want to know the order of these in the event that they do that. The next step then is analysis or interpretation of the research. This is where you do your statistical manipulation. This is where you get your means, the medians, the modes, the standard deviations, the two-tailed t-test, the ANOVA, analysis of variance. You've got the Pearson R. You've got a lot of different statistical tests that you can run. You put your data in and you run these different tests to get this kind of information. This is where you really need to make sure that if you're working on a public health team, one of your team members is a statistician. Statisticians are a whole different animal, and most of us, we can collect the data. We're clinicians, we collect the data, but then we don't exactly know what to do with the data beyond like a mean, a medium, and the mode. So we want to know more information, but how to put it into the computer and get that out so that it tells you something about this vast amount of data that you've collected. This is where you need the statistical animal who knows that stuff. You can tell them, this is what we've got, this is what we want to do, how can we go about doing this, and they know what to plug it in and what tests to run. Then you have your presentation of results and your scientific method. With this step, you actually are reporting. You're reporting the mean, the medium, the mode, your standard deviations. You're reporting this information. You're talking about if there was a critical incidence, if you did a time series, you report all of your results. And then the last part, the last step is the conclusions. In true research, this is the only area in this research report that a true researcher can give or express an opinion about a relationship, about what happened or what didn't happen in terms of why the hypothesis was accepted or why we said that there was a relationship, there wasn't a relationship. This is the only area. Whereas if we're looking at programmers are getting up here and they're, they develop their research plan. And if they're saying that XYZ reduces or can reduce the symptoms of the coronavirus, and they see XYZ is not doing it, they want to find something that's going to work. A programmer will do that process eval, and they'll say, okay, this is not working. We're not going to take this out 6 weeks or 12 weeks and just start and then find out at the end of 12 weeks there's no relationship here, there's nothing going on. They're going to try to manipulate it at that point in time because they're interested in making the program work. So let's look at the statistical analysis of the data. How are we going to do this? When we talk about statistics, it's a science that describes or summarizes or analyzes, interprets this numerical data for the purpose of making an inference about a population. When we talk biostatistics, we're talking about biological sciences. That's where we're talking about diseases, cures for diseases, treatment, prevention, this type of thing. So there are 2 major branches of statistics. You've got descriptive statistics, which remember we've already talked about descriptive type studies, descriptive type research, where basically you're just describing and summarizing data that's collected with no attempt to generalize it beyond the immediate sample. So you have your sample selection and you get the mean, the medium, the mode of that group, that smaller sample, and you're describing about that particular sample. That's descriptive. Whereas inferential, there is another set of tests that you can run where that takes this information about your sample, and that's used to generalize your sample findings to the entire population that you're looking at, to the population from which the sample came, all right? Which of these you run, whether it's descriptive or inferential statistics, is going to depend upon the type of data that you've collected. And there's 4 levels of data. There's nominal, ordinal, interval, and ratio data. And these 4 levels can be divided into 2 major measurement categories or classifications. You've got categorical, or also called discrete or enumeration data. With this, there's no mathematical relationship between the numbers or the data that you've collected there. And that's going to be nominal data and ordinal data. And to remember that. And to kind of throw out some other things that they may be asking you, there's no parametric, this is not parametric data. Okay, it's non-parametric, meaning that it's distribution free. I couldn't take this data and put it on a plot and then show that I had an increase or a decrease the longer I went through the particular study. We counted in whole numbers only, and it's considered quantitative, okay, in nature. Remember, with the statistics, we really want quantitative, not qualitative. And so what we're talking about categorical or discrete data, it's qualitative in nature. It's going to be something that it can orient us to. It can kind of be there's the simplest level of measurement. Basically, what you're trying to do with nominal and ordinal data is just try to get your data in some type of an organization. Trying to divide it up into some kind of grouping so that you can go from there and go into the, collect the kind of data from these individuals that becomes quantitative, that has a mathematical relationship. So continuous data, or a lot of times it's called measurement data, there are mathematical relationships, okay, between the elements of in your sample, between the variables, the elements, the numbers that you collect in that sample. And interval and ratio data is continuous or measurement type data. It is parametric, meaning that you've got a normal distribution, you've got a variance. So you could say that this number varies from the other numbers by this much. You guys look at this, mathematical or continuous type measurement in that, you get a mean. And I'll report on your exams, you always look to see what your exam is, and then you look to see what the average or the mean exam is, and then you look to try to determine how far does my grade fall from the average, or how does my grade compare to everybody else's in the room. You're trying to look at mathematical relationships in this point in time. Okay, so let's talk about the data that we're looking at here, nominal, ordinal, interval, and ratio data. Nominal, I think N for nominal, N for naming. That basically what you're doing, it's the simplest form of measurement, it's the easiest form to kind of organize your data, where you basically just divide your data up into groups and you name the groups, like group A or group B, or boys or girls, or blue-eyed versus brown-eyed. First year dental hygiene students, second year dental hygiene students. You're just naming something. Whereas ordinal data, then, you're trying to rank or put your nominal data into some kind of an order. You're ordering it. There's still no mathematical relationship between these. So if I was to take, my blue-eyed and my brown-eyed individuals, and in my blue-eyed group, I want to put these guys in some kind of an order. So I'm going to say, okay, here's the blue, here's the bluer, and here's the bluest eyes. There's no mathematical relationship between blue and bluest. I'm just trying to get some kind of order there. If I take you in a classroom and I have you number off 1, 2, 3, 4, 5, that is what you're doing, is basically there's not a mathematical relationship between number 1 and number 5. I'm just trying to organize things. That's the ordinal. If you say large, medium, small, and extra small, again, extra small is not 5 times smaller than large. We are just there trying to say, okay, we're going to put this in some kind of an order. Now, when we get to interval data and ratio data, that's where we have mathematical relationships. So with interval data, this is a basic standard intervals, or they're equal intervals between variables, right? But the thing to remember with interval data is there's no true 0 point. So in other words, what happens, the easiest thing to think about with interval data is that there is a mathematical relationship, but there's no true 0 point. Because the same thing we're going to say for the ratio is there is a mathematical kind of interval scale, except there is an absolute 0 point, okay? Meaning a total absence of something. So the easiest thing when we talk about interval is think about a thermometer where you've got negative 20 degrees, negative 10 degrees, and you've got 0. Then you've got 10 degrees, 20 degrees, 30 degrees, 40 degrees. There's that 10 points of temperature between those, but there's no absolute 0 point. There's no 0 level. That 0 degrees doesn't mean an absence of temperature. When you think about ratio, again, we've got interval scale, but there's an absolute 0 point. So I always think in terms of interval along the lines of weight. You can have, if we talk about weightless, basically 0, 0 pounds versus 10 pounds. You add 10 pounds to the 10 pounds and you get 20 pounds. You add another 10 pounds, you get 30 pounds. Okay, so there's that relationship, numerical relationship between them, but there's no absolute 0 point. Can say the same thing about height. Even though, if we have 0 height, that means basically that we don't exist. There's nothing there. Whereas if we say, on a ruler, if I've got 1 inch, okay, and that 1 inch equals that particular value, I add that value to that 1 inch, and now I have 2 inches. And we can say 2 inches is 2 times that 1 inch. So you can see there's a relationship between them. So let's look at some of the classifications of some of the type of data that's out there and whether it's going to be nominal, ordinal, interval, or ratio data. If we talk about G.V. Black's Carey's classification, where he's got class 1, class 2, class 3, class 4, is there a mathematical relationship between class 1 and class 4? Is class 4 4 times as good or as bad as a class 1? No. Basically, G.V. Black said, okay, class 1 is this, class 2 is here, class 3. He could have said class A, class B, class C, class D. He could have said good, bad, ugly, really ugly. All right. So with this, we're actually looking at nominal data. How about your blood types? A, B, O positive, etc. Is there a mathematical relationship between A and B? No. We could have said instead of A and B, we could have called it 1, blood type 1, blood type 2, blood type 3. So again, what we're looking at here is nominal data. OHIS scores, 1 through 6. Would we say that's nominal, ordinal, interval, or ratio? First thing you have to ask yourself, 1 through 6, is an OHIS score of 1 6 times less than a score of 6? No. Okay, we're trying to organize. That basically tells us how much garbage we have on the teeth. And we're trying to say, okay, here's dirty and dirtier and dirtiest and really dirty, but there's no mathematical relationship between dirty and really dirty. We're just trying to take what? We're taking nominal data and we're trying to put it in some kind of, we're trying to organize or order the level of debris on two surfaces. So this is going to be ordinal. What about Engel's occlusal classification? We've got class 1, class 2, class 3. Again, is there a relationship? Is class 3 times as bad as class 1? No, he's basically is doing what? He's naming it. Whoops. There we go. We're naming it. Now, faculty evaluations, where you guys have to select you strongly agree, you disagree, or you strongly disagree. When we look at strongly agree, these things are all subjective type information. You can't take this and plug it into a computer. What you have to do with this is you have to quantify it. You have to assign something. And so what we're basically doing here is we're going to say, okay, 4 for strongly agree, 3 for agree, 2 for disagree, and 1. We're trying to put this in order of how someone feels about a particular thing. But is there any mathematical relationship? Can we say strongly disagree is, a set mathematical 4 times less than a strongly agree opinion? No, we can't. If we had just strongly agree, disagree, and strongly disagree, that would be nominal data. But by trying to plug in a number, that makes it ordinal data. And with that ordinal data, then we've at least, it's still subjective data, but we're trying to quantify it make it a little bit more objective so that we can plug it into a computer and we can get some statistics regarding it. Okay, so we are at the end of our time frame here. I will pick it up again in the next hour. We'll finish this, and then I think we'll move on to the next section of this, which will move us into the next topic area that we'll be looking at. So if you have any questions, feel free to email them to me. I'll try to answer them. Or if we have to, we can go on a live Skype where you actually can see my face. And that's not a good thing, but we can take that particular method of instruction also.